Hi, Year 10s. So today what you're going to do is look at graphs of polynomials. We'll do this over 2 lessons, so this will be the first of 2 lessons. Okay, so what the notes do first of all is get you to explore the differences between the standard parabola. This one here we call that the standard inflected cubic, and this one here we call this the standard quartic. Right? Now let's have a look at the standard parabola first, because that's the one that we're most familiar with. So we'll start it by using this table of values. So we'll square 0 first of all, which is 0. Now we'll square a half, so a half times a half. Oops, thought of the answer as I wrote that. A half times a half is a quarter, so that's going to be a quarter. Now this one here, all that's going to do is it's going to square the negative a half, so that's going to be a quarter as well. Square 1 and you get 1. Square negative 1 and you get 1. Square 2 you get 4. Square negative 2 you get 4. Right, let's put those points on the Cartesian plane. So it starts at the origin. And then we've got a quarter. So here is 2. So this is 1. This is a quarter somewhere down here. It's not really a great scale to work with. Now 1 is 1. That's somewhere there. And 2 is 4, so that's 2 and 4. All right, and it's going to be the same on this side, so a quarter somewhere down there. 1 and 2. All right, so if we try to draw our parabola, this is going to be a little bit mediocre here. In fact, I'm going to pause it and draw it, just so that you don't have to watch me stuff it up. Okay, so there it is. So got the shape of the standard parabola there. Now, what we're going to do is look at the standard inflected cubic. All right, now I'll talk about that word inflected in a second. So let's go and cube 0. So that's going to be 0. Now when we cube a half, that's a half times a half times a half, which is 1/8. Now when we cube 1, that's 1 times 1 times 1, that's just 1. And when we cube 2, we get 8. So what we can see here is between 0 and 1, the values are smaller than the standard parabola. But then after 1, what's going to happen is the values are going to go faster. And I'll just demonstrate by putting 3 in. So 3 squared is 9, whereas 3 cubed is 27. So when you cube numbers above 1, what's going to happen is that they're going to grow faster than when you square numbers. And that should make sense to you. Okay. Now over this side, now what happened with the parabola is that we got the same y values for these two different x values. Now what's going to happen here is that when I cube negative a half, that's going to be negative a half times negative a half times negative a half. Now what we're going to get is an eighth. Now negative times a negative is a positive, and then when you multiply this other negative again, you're going to get a negative answer. So this is going to be negative 1/8. Now here, when we cube negative 1, it's going to be negative 1 times negative 1 times negative 1. That's negative 1. When we cube negative 2 times negative 2 times negative 2 is going to be negative 8. So the rule is that when you cube a negative number, you'll always get a negative result. That's a guarantee. Whereas when you square a negative number, you're always going to get a positive result. All right, so let's just graph this. So again, this is a little bit hard to graph on this Cartesian plane because it's going to go through 1, 1. The cubic's going to go through 1, 1. And I need to plot a point that's less than a quarter. So it's going to be a bit lower than that. Okay. Then we're going to do 2, 8, which is somewhere up there. All right. Over this side, we got negative an eighth. Then we got negative 1. Then we got negative 8 down there. All right. So the way this is going to work now is the cubic will follow this pattern here. It'll go through negative an eighth. And it's going to come through, and it should be lower than the parabola there, so that's a bit of a mistake. And then up, like so. And this point here, where the cubic sort of comes in and flattens out and then goes back up again, we call that a point of inflection, okay? And later on we'll refer to it as a stationary point of inflection, but more on that later. Okay, the last one is a quartic function, so a power 4 function. So let's power 4 0, and that's 0. When I power 4 a half, that's a half times a half times a half times a half. That's going to be a 16th. All right, then I power 4 1. That's 1 times 1 times 1 times 1. It's just 1. And when I power 4 8, I'm going to get 16. Now what happens on this side? Now because it's an even power, just like power 2, what will happen is that the number of negatives over here, okay, will be even, which means that will always turn out to be positive. So negative a half to the power of 4 will be negative a half times negative a half times negative a half times negative a half. Now negative times a negative is a positive, times another negative is a negative, times another negative will be a positive. So the rule is that when I power 4 a negative number, I'm always going to get a positive result. So negative 1 power forward is going to be 1, and negative 2 to the power of 4 is negative 16, no, positive 16. Okay, so let's just draw that. So I've got 0, 0 at the origin. Now I'm supposed to plot 1/16. It's going to be even lower. All right, then I'm going to plot 1, 1. So back there again. And then I'm going to plot 2 and, what is it? 2 and 16. 2, 4, 6, 16 is there. Okay, so the same on this side. So it's got to be a bit lower, somewhere down there. 1, 1, or negative 1, 1 rather. And negative 2 and 16, so up there. So again, what we notice that these power 4 functions, the standard quartic function, is going to look very much like y equals x squared function. And that's actually the same. It'll be the same for y equals x to the 5, except that will look much like this. But again, more on that later. All right, let's draw our graph. So it's going to be flat through there. It's going to come up. So it's hard to delineate a little bit between them. That'll do. All right, so there's our different graphs. So this one here is y equals x to the 4. This one here was the inflected one, y equals x to the 3. And this one here was our old friend, the parabola. Okay, so describe the features and shape of each graph. Well, it's really best summarized down below, so I'm not going to worry about answering this, but the difference between these two here, okay, what we're going to say is that the difference is between the values of negative 1 and 1, x to the 4 values are less than x to the 2 values. So between these two values here, it's less than. Now, when x is greater than 1 or x is less than 1, x to the 4 is larger than x to the 2. What I'm suggesting there is when you power 4 a value greater than 1 or less than negative 1, I should have said, then this value here will be larger than this value. Now, when x equals 1 or x equals negative 1, they are equal. So they intersect. Where do they intersect? At negative 1, 1 and 1, 1. They're the two intersection points. So yeah, after all that, these are the actual sketches. Much easier to do it on the calculator. You can see kind of the flatter bottom of the x to the 4 versus the x squared function. Okay, we won't worry about this second one here. That's a different type of cubic, and we'll look at them later on. So in summary, okay, what you've got here is the basic x to the 3 function. So this, I call this the standard inflected cubic, because there's other kinds of cubics other than the standard. This one here, I call this the standard quartic. Okay, and it's very similar to the standard parabola. Okay, so to sketch cubic graphs in factorized form with 3 different factors, what we do is we use the null factor law. Okay, so that's just like quads, okay, where possible, and if it's been factorized, we use the null factor law. Okay, what we do then is we find the y-intercept, okay, and we connect to work out whether the cubic is a positive or a negative cubic graph. Okay, now, if we know that we've got a positive cubic, all right, when we draw it, it always starts with a positive gradient. So you can see this cubic here has started, when the person's drawn this cubic here, it started with a positive gradient. Okay, now how do you know the coefficient of the x to the 3 is positive? Well, imagine you expanded this. You would do this times this times this, which would give you an x term of y equals x to the 3 with a 1 in front of it. Now that value there is positive. All right, so positive cubics start with a positive gradient. Now negative cubics start with a negative gradient. All right, and now how do I know that this has a negative first term? Well, we're going to do x times x times x, which will be x to the 3, and the result is going to get negated. Now, I don't know what all the other terms are, but I know that if I expanded this, the first term would be negative x to the 3. All right, and notice that when it's drawn, it starts with a negative gradient, so it slopes downwards, whereas this one, positive cubics, start by going upwards. So we're going to apply this rule to all of the cubics we see. So positive cubics start with a positive gradient, negative cubics start with a negative gradient. All right, now these things here, this part here and this part here, these are called stationary points, okay? Now they are not located symmetrically between x-intercepts. So what I'm suggesting to you is that this turning point here is not at negative 2.5. We'll look at this a lot more later on. We use calculus and things like that to help us find these stationary points. That won't be a thing that we do this year, so we're not going to worry about that at the moment. All right, so here are some different types of family members of cubic functions. All right, so this is point of inflection form, and you'll notice that this form here looks very similar to what we call, oh gosh, I forget the name, with a parabola. It's called turning point form. So this looks very similar, except the only difference is we've got this power 3. Now remember, what this means is this value here shifts the cubic h units to the right, and this k value shifts the cubic k units up. Okay, so what you can see is that this is the standard inflected cubic moved h to the right and k units up. All right, now if it's given to us in this form here, linear factor form, we can see that we've got each of the linear factors, x equals L, x equals M, and x equals N. And because we're assuming it's positive, bad assumption because we don't know what A is, but we're assuming it's positive, then we can see the result. All right, what to do when we get this repeated factor? Okay, well again, if you think about this via the null factor law, if we solve this if p of x equals 0, we'd get x equal m. But it would come up twice because this really looks like this. P of x equals a, x take m, x take m, x take n. So because this factor comes up twice, what actually happens is that we get the cubic turning on the axis itself. Okay, so that's what's going to happen there. So whenever you see a repeated linear factor, we know that it turns there. Now, how to work out whether it turns like this or like this, I'll explain. Okay, in this final one, we kind of saw this in class today where we had this irreducible factor form when we couldn't factorize the quadratic, okay? And what's going to happen is, generally speaking, they look something like this. There are variations, but that would be good enough. Okay, so what we're going to do is sketch it. Okay, so the way we'll do it is we'll first of all get the x-intercepts, and they occur when y is equal to 0. Okay, so via the null factor law, we're going to say x equals negative 3, x equals 2, and x equals 5. So let's pop them in. We've pretty much got most of what we need. So there's the first one, negative 3. There's 2, and there's 5. All right, so what we're going to do is get the y-intercept now. Now, the y-intercept occurs when x is equal to 0. Okay, so we're going to go y equals, and we're going to put 0 in there, which leaves 3 times 0 goes in here, and we get negative 2. 0 goes in here, and we're going to get negative 5. So that's going to be y equals negative 2 times negative 5 is positive 10. Positive 10 times 3 is 30. So it's going to be off the charts somewhere up here. Okay. All right, so this is a really kind of badly drawn question. So I'm just going to get rid of these numbers here. Let's pretend that the numbers actually didn't exist. All right, so get rid of them. All right, so we're going to pretend that this is an unscaled axis, and what we're going to do is draw this first cubic here. Okay. All right, so what's going to happen is that when I expand this, I'm going to get x times x times x, which is x to the 3, and it's positive. So positive cubics start with a positive gradient. So what we're going to do is start it with a positive gradient, go through this x-intercept, and what it would do is it would go up, turn at 30 somewhere up here, it's going to go back down and come back through there. That's how this cubic is going to look. But because we haven't got this scaled, we just send it through one of those y values. So here we go. We're going to go up through there. We're going to turn. We're going to come back down. I'm going to turn back and go through there. And we've got our cubic function. So let's mark the point there and go, that's 0, 30. This point here is 5, 0. This point here is 2, 0. And this point here is negative 3, 0. Okay. All right, let's do this one here. So what about this one? All right, so null factor law, 0 equals negative x, x plus 1, x take 3. Okay, that means that x could be 0, x could be negative 1, and x could be 3 via the null factor law. So that one there is just negative x equals 0, x equals 0. So let's pop in our x-intercept. So there's 1 at the origin, 1 at negative 1, so there, and 1 at 3. All right, now we'll do the y-intercepts. And because it goes through the origin, I already know that the y-intercept is going to be 0 as well. Okay, so the final step with this one here is we've got to then draw this thing. Now, when we expand this, I'm going to get negative x times x times x. That means that the first term is going to be y equals negative x cubed, which means it's got or has to be drawn with a negative gradient to start with. So our gradient comes, or our function goes through like this, will come up and then down. Now, you might be wondering, how far do you go up or how far do you go down? It doesn't matter at the moment. In year 11 methods, what we do is we show you how to get these 2 points here. You could use a calculator to do it if you wanted, but we're not worried about that. So as long as you've got the x-intercepts and the right overall shape, that is, starts with a negative gradient and goes through, then you're going to get full marks in year 10. Okay. I'm not going to do this one here. What I'm going to do is 2 more examples. So give me a sec. So the next 2 examples I'm going to do, these aren't in your notes. I've just included these because you're going to end up doing or being asked questions like this, and there's no examples of them. So I thought I'd better do 2 more examples. So this one here, what I'm doing is I'm looking at this cubic here and I'm going, ooh, this is just the standard cubic, okay, which is y equals x to the 3. That's that one that looks like this. And what's happened to it, just like a parabola, we read this just like a parabola, it's moved 3 units to the right, so 3 units right, and 1 unit up. So what that's going to do is take this stationary point of inflection or point of inflection, move 3 to the right and 1 up. So let's do that on here. So we're going to go, here's 1 to the right, 2 to the right, 3 to the right, and 2 units up. So our point of inflection is going to be there. So I know that basically this graph here is going to go something like this. Now it says we don't need to worry about the y-intercept, and it's probably because it's really low. Actually, let's try it. 0 goes in, negative 27, negative 26. Yeah, it's just too low. Okay. Right, but let's get the x-intercept, and that occurs when y equals 0. So we've got 0 equals x take 3 plus 1. We're going to take away 1. All right, now here's an interesting case because what we've got is this is raised to the 3. I forgot to write that in. Now, what's the opposite of power 3? Well, it's going to be the third root. And what we're going to do is third root both sides. Now, the third root of -1 is the value that when multiplied by itself 3 times equals -1. And that's going to be -1. And that's x take 3. So what we've done is got rid of or undone the power 3 by doing the opposite of power 3, which is third rooting. Okay, now what we're going to do is add 3 to both sides. So plus 3, plus 3. We're going to get x equals 2. So our x-intercept is at x equals 2. 2, 0. And this stationary point of inflection is at 3, 1. So let's try and draw this thing. So it's going to go something like this. And up. Excuse me. So it should be roughly symmetrical. Okay. But we've got everything we need for this one here. So again, the key is to recognize that this is in inflected form. Okay. The final one, this is the last example that we'll do, is a repeated factor. Okay, so here we've got a repeated factor. So p of x without that repeated factor would look like this, -x, x take 3, x take 3. Now if I go on to use the null factor law, we're going to get -x equals 0, x equals 0, and x equals 3. And that's the repeated factor. Right, so let's put in our x-intercepts, which are at 0 and are at 3. All right, now let's find our y-intercept, which of course is going to be the origin, because when I sub y-intercept occurs when x is equal to 0, we're going to get 0 times whatever this is, which will be 0. So the final thing that we need to be aware of is, how do I draw this thing? So is it going to start with a negative gradient or a positive gradient? And to work that out, what I need to do is imagine, when expanded, what the coefficient of the cubed term is going to be. So that's going to be, when expanded, is going to be x squared, and then that gets multiplied by -x, giving us -x cubed. So this is a negative cubic, which starts with a negative gradient. So what I'm going to do is I have to go negative gradient through here. And then what's going to happen is we've got a repeated factor. We're going to come up and kind of bounce off the ceiling here, or bounce off the x-axis. So start with a negative gradient, turn somewhere down there, bounce, and go back down again. 3, 0, 0, 0. We're not worried about this stationary point here. This axis isn't even marked, so it doesn't matter where that stationary point is. And we've got our graph. Okay, so from here, what you're going to do is just jump onto the OneNote and check carefully what the questions are that have been set, because I'm going to do this, as I said, over the space of 2 lessons. Okay, so this will be the first of 2 lessons, and then we're going to cover a few more things in the second of 2 lessons on graphing polynomials. So good luck with that, guys. I hope it goes well, and I'll check in with you later on in the week.